I'm pleased to be here, and I'm particularly pleased that the organizers allowed me to talk about foundations. So you may ask, what does quantum foundation have to do with a program or a school that is about quantum information? And in fact, one could say that it's now a good time. By time, I mean not right now, but maybe the age of quantum information is a good time to go back to old questions that have been asked by the founders of quantum theory. So in fact, many of the questions we are going to discuss in the next 3 lectures, from today until Wednesday, are questions that came up already in the very early days of quantum theory. But then quantum theory turned out to be so successful and so accurate, and it just worked, that at some point these foundational questions got a bit forgotten. I mean, there were always people looking at them, but the majority of physicists thought, okay, this theory just worked. Why should we hold us up with questions that sounded to be just of philosophical nature and didn't have an impact on actual experiments? So I think for a long time there was only kind of a small group of people who really cared about them. But now, as people started to study quantum information, there are several reasons why foundations is again becoming more and more popular. Actually, it's really becoming very popular if I compare the situation when I started working in quantum information, maybe 10 years ago. It was quite exotic to talk about these things. There were some people who liked these questions, but most of them said, you shouldn't even work on them because this is just good for your career. So I worked on quantum cryptography, but as you will see, this is very closely connected to quantum foundation. So what is the reason why we should now go back to these questions? So there are actually 2 very important reasons. One reason is that if you do actual applications like quantum cryptography, questions about the foundations just come up and have to be answered. So we will go into that, but one example is the question about the completeness of quantum. This is essentially the question whether the mathematical formalism we have today, the wave functions and so on, are in some sense a complete description of what's going on. And this is important if you want to argue about the security of quantum cryptography, because of course if this was not a complete description, then it could be that an adversary has some additional information which is just not covered by the formalism. And this would be highly problematic for security proof. Also, when you talk about randomness generation, of course, if something is random in quantum mechanics, but quantum mechanics is not complete, then it could be that it's actually not very random and you just have not a good enough description of these things, and it looks random because there's just not enough elements there to describe what's going on. So that's one reason. So to actually study applications, it's necessary to do foundation. So you see, my choice of working on cryptography initially was not so far away from that. Then the other reason is that now we are developing technologies that allow us to control complex quantum systems. And certain thought experiments, or things that were called thought experiments because it looked completely unrealistic to realize them, are now actually becoming implemented. So there are, in principle, experiments we can do to test certain questions that have been asked about the foundations of quantum. And I will also go into that, so this was just a small overview. And in fact, I don't think I should bore you now with a long introduction. I would just like to start with a very simple example. Actually, the example is so simple that almost any experiment you do in quantum theory is somehow a version of this example. But many of the questions that we are going to discuss already arise in this very basic example. By the way, I will do everything on the blackboard, so I will in that sense go relatively slow because I'm not very fast in writing. But please interrupt me whenever there are questions. I'm quite flexible with the program. That's the advantage of a blackboard. So I really encourage you to kind of tell me whether I go slower or faster. So that's all up to you. Okay, so let me start with this very simple example. Okay, maybe I should just warn, and as a simple example, it will at the beginning really sound to you as if you know that all extremely well. But ultimately we will come to a point where, at least as far as I can see, there are questions to which no one has an answer. So we'll start with something that is extremely well known, but at the end, maybe not of today, but certainly tomorrow, we will arrive at questions where there are no answers. And so in that sense, you should really see this whole lecture also as something like a preparation for possible research. So that's something I forgot to say, which is important, that in quantum foundations, there are questions, and in some way, I mean, not philosophical questions where one could never find, or really maybe where it's not so well defined what the correct answers, but actual physical questions that are unanswered, and which are nevertheless in some way very central to quantum mechanics. And so in some way you could see this whole thing as this whole course as a preparation for those who may want to look into these questions. And they're really questions about quantum mechanics, they're physics questions, and not kind of try to, it will not be a name of this course to convince you of some interpretation that we make. It's really about physics in that sense. And by the way, there, just that you see the connection to current research, you may have heard about paradoxes that people currently study. For example, the black hole information paradox. That's something where we try to think about thought, or we have thought experiments where at the same time quantum mechanics and gravity enter. In this lecture I will not go into gravity. Maybe if I have some time at the end I may say a few things about that, but I will stick with quantum theory without giving too much importance to space-time. But as you will see, even then, even before we start to mix quantum mechanics and gravity, there are unanswered questions. Maybe they have to do with these paradoxes. Clearly, if there are paradoxes already in quantum theory, it's not surprising that if we combine it with another theory, there are still paradoxes. Maybe not. Okay, so what is this simple example? So the simple example is just, I consider a very basic experiment where you have some system which I call S, and you could think of this system as a spin particle, spin 1/2 particle, that you may control, and I will only look at the spin degree of freedom. Of course, the particle has also position and so on. I will only look at that. And we will look at another system, or maybe rather a device, D, which is a measurement device. This device for measuring let's say it's a particular direction, let's say the vertical direction. I call that Z direction of the spin. These are two systems that we actually have in a lab. And now the simple thing we can do with these two systems is to prepare a spin and let it and apply the measurements that this device can do. And the way I'm going to talk about that is I will in some way say there is a time t0 in which we prepare a spin before the measurement, and there is a time t1 in which the measurement has been completed. And now, this is very simple. So for the moment, there is nothing special. It's more maybe a way to introduce notation that I'm going to use later. We could prepare the spin in some direction. Let's say, for example, up. I just maybe I write here preparation of S. And let's say that in the up direction, that's a possible direction. And now we have, in some way, a time evolution from here to here. Measurement is a particular type of an evolution of the physical system. And after this evolution, these systems are in a certain state. So actually, maybe to be more precise, I should say this is the spin that is prepared like that. But let's also think about the measurement device being prepared for the measurement. So I could say maybe the measurement has different states in which it can be. For example, it can be in the state where it hasn't measured, where it's ready for a measurement. I could call that state the ready state. And then after the time evolution, the spin, if I measure the up-down direction, and I assume this measurement is non-destructive, so the spin is still up if it started to be up, but the measurement device now shows a particular result. And let's maybe say it's measured, and it's now in a state where its display shows that the spin was plus 1/2. Now, of course, I could have prepared the spin downward, and with the same setup, the outcome will be that the spin is still downward, but the measurement device shows minus 1/2. So that's what we can do. We also know what happens if we do another preparation. We know, for example, that we can, let's say, prepare the spin to the right. Spin to the right you can see as a equal superposition of up and down with a certain sign. I will make that more precise in a minute, but let's just think of this as spin right. So if I measure the spin right in the up-down thing, then we know we end up with one of these cases. And maybe I should say 1/2 of the cases. So let's suppose I repeat this experiment, and 1/2 of the cases I get that it's still up and z is plus 1/2, and in the other half of the cases I get the opposite. So that's extremely well known. That's just a description which is now almost independent of any quantum formula. I just described what actually happens if you do that experiment. So I guess everything is clear here. Now what I'm going to do next is to tell you how I formalize this in quantum mechanics. This is not going to be a big step, but the point will be that there will be two ways of talking about this very same experiment. So the first, wait, maybe I do that on a different platform. So this is now let's say the quantum theoretical. Okay, I don't always want to write quantum theoretical. I will abbreviate that as QT for quantum theory description of this experiment. What's that? So there is one option I have, which is maybe the most natural thing you would do if you describe that, is to say, the spin S, you really modeled that as a quantum system. And not have to go into much detail here, I guess, because you're very familiar with what I mean when I model a spin as a quantum system. But I could say that the Hilbert space, so I have a Hilbert space that I associate to the spin with bases. Let's say one possible basis is that it consists of some up het vector and a down het. That's a way to model this thing. Now, the device D, I could model kind of as a classical system. What does this mean? I just describe it as a system that can be in three perfectly distinguishable states. In some system, or I just say it's three what I call classical states. So maybe you could think of this as just values, and what are they? So one state would be ready, it is a set, or one state would be that it has measured plus 1/2 and minus 1. Of course, an actual measurement device has many more different physical states. For example, if I heat it up, it's kind of in a different state than when it's cool and so on. But I'm interested in, you could see that these are classes of actual microscopic states that I'm interested in. Okay, now that's the usual description, and if I work with that description, I will in some way use the usual formalism, which is Born rule and so on. But before doing that, let me just first say that I have an option in principle. I could do the following. I could again model S as a quantum system, and then as above, so as in 1. But I could also model the device D as a quantum system. So the idea being that, of course, a measurement device is after all also a physical system. So there's nothing that forces me to kind of not, or that forbids the use of quantum mechanics to describe this system. So now, of course, this system has a huge Hilbert space. But let's suppose that we are only interested in a certain, let's say, degree of freedom or a subspace or in some way of that. And I could say that I simplify that and say there is a Hilbert space with bases. Or maybe, I mean, if you want to be more general, you just don't need to write bases. You could say these are just three states out of a basis, and the space is much larger and has many more elements. But just to simplify the treatment, and it doesn't change anything because we'll keep saying this subspace, we can talk here about the basis. And of course, one basis state is now corresponding to this ready state. Another basis state is that the device shows +1/2, and maybe a third one is that it shows -1. So these classical states are now just vectors in a Hilbert space. So these are two possible descriptions. Now, what do I do in these descriptions? Maybe I write that here again. So what happens here? So in description 1, what I would typically say is that at time t0, the system is described by, let's say, a state up. So I write here now indices to say this is the system, the state of the system S, and the measurement device. This is not quantum mechanically described, it's ready. This is for device T. And then there is this time evolution, and that T equal 1, and the spin state is still that, and the measurement device. So this is almost the same as what I wrote before in the classical description. But, okay, maybe just for completeness, I should write that because I will need this later. Of course, if it's down, the same happens as before. So the only thing is that I have now a ket here, which I didn't have before. But also, if I have an arbitrary state, let's say I have some vector phi, which could be a superposition of up and down with some coefficients alpha and beta. That's maybe the most general pure state I could assign to this system. Then what happens here? So here I cannot directly deduce that from here. I need an additional rule. That's now important to see because that's different, by the way, in the second description that we will see. So I cannot, if I know these two behaviors, I don't a priori know what happens for this state because that's just a different state. And so here we apply, of course, the Born rule. And the Born rule will tell us that with probability, which is given by, let's say I write it here in this form, take the overlap of phi up squared, which is of course in this case alpha squared. And with this probability, I will again end up in this situation as before. So as I said, these things are extremely simple so far. And this is just the opposite. The probability beta squared, I will end up with that situation. This is the Born rule, and by the way, I also applied what is sometimes called Luther's rule. Luther's rule is that if I apply a measurement, what's the state of a projective measurement, what's the state of the system after the projection? And to write down here and up, I applied that. But that's just a remark so far. That's not so important to know. Maybe some people know quantum mechanics very well, but have never heard the name Luther's rule. So that's really that rule that just tells you what is the post-measurement state. And the Born rule is the rule which gives you this probability here that you're also very familiar with. Now, the second way of describing it looks, again, very similar. But here, because both things are now a quantum system, I would write this as that. So that's the initial state at time t0. And the final state of the system in this particular case is, now it's just a ket instead of, so here I have essentially no difference except that the notation looks a bit different because I now have a ket for the device. Before I didn't have a ket for the device, but just a so-called, or to think of it as a value of a random variable. But now, for the third thing, okay, in some way you also need an additional rule, but the rule is now a different one. Here the rule was the Born rule and Luther's rule. Now in the case, in some way Luther's rule is already used upstairs, by the way. But I need here the Born rule. maybe I write that here. That's really Born rule. Here I need something different. So if I have this initial state, some phi, S, tensor ready, E. So by the way, does anyone know what rule I would apply here? I mean, if I wrote here Born rule, what should I write here? What's the rule I apply here to infer what I should write on the right-hand side? Do you have any idea? Yes, right. I should just write linearity. That's the quantum mechanics is linear. I mean, you could say it's unitary, but a unitary is in particular linear thing, which means if I now apply linearity, this is just a superposition of two states. So let's suppose this state is the same as above. Then the final state will be alpha up S, and the measurement device shows plus 1/2 plus with the coefficient beta down S Z is equal to minus 1/2. And so maybe I write here D. Okay, so that's the situation that we had in the second approach. Okay, so far, as I said, this is extremely simple. There was nothing special going on up to this point. Yes? Right, that's a good question. So when I said here linear, you could also think of, I just apply the Schrödinger equation with a Hamiltonian that describes the mechanism of the measurement device. Now, people in quantum information, they have a simpler way of saying that. They say a measurement device is essentially almost a controlled knot operation. Not precisely that, because I have here the ready state, but I could also say initially it's kind of state plus 1/2, just as a convention. And then it's a controlled knot. And now you could say any possible implementation of a controlled knot. I mean, there are many Hamiltonians, or many actual physical devices that do that, would be valid Hamiltonians to generate this evolution. But the important thing here is, so what's the difference between these two things? I just took a different view. And this is now already a question that was asked very early in quantum theory, and it's also sometimes known as the question of the shifty split. And by the split, people meant the distinction between where do we put the boundary between classical and quantum systems. So in both cases, clearly the spin is a quantum system. And we need to do that because we initially already want to prepare it possibly in a superposition, which is something we couldn't even describe with a classical system. But then the question is, you have this measurement device, and do you now put the split between classical and quantum in between the system S and D? Or do you say, no, actually we could look at the whole thing from the outside. We are still outside of the measurement device, and we put the split outside of S and D. So maybe schematically you could say, one thing is here, the split is here is D, and here are maybe observers again. I mean, here are V, so to speak. That's one possibility. That's kind of the version 1. And the version 2 has, so this is the split, or the cut, sometimes called the cut, Heisenberg cut. So when you read this term Heisenberg cut, it's exactly, they mean that thing. Sometimes it's Schrödinger cut. So, okay, you see, this is another cut. These are two choices of the cut. And by the way, when the early, where the fathers, there are not so many mothers, but fathers and mothers of quantum mechanics discussed this question, they had very different opinions about where we could put the cut. So already in this example, there was not an agreement what to do. And for example, there were people like Schrödinger, and you know the famous Schrödinger cat example, where he said, the cut, this could be, so it's natural to, if you replace the measurement device by a cat, then you have essentially the Schrödinger cat example. So even if you don't know what if you have not heard of it, just think essentially of the measurement device as a cat who looks at it. I mean, Schrödinger was a bit more brutal. He said in one case she dies and in the other not. But you could just think of a cat that observes the outcome of the spin measurement. That's the more animal-friendly version, and then this is that here. So Schrödinger said, of course, this cut can be outside of the cat. And there are others like Wigner, and I will come to that, who were more skeptical and said, no, there must be some, so if a big classical system involved, or at least a living object, then this cut cannot be outside of this living object. And then, for example, Bohr, actually, when you read the literature, Bohr had different opinions at different times. He had discussions with Heisenberg and so on, and this influenced, or maybe he influenced Heisenberg and so on. So there's a whole history. It's not so clear what he would say about it. But you see, this is not, there was no answer to that. Now today, you see, this is maybe one thing that becomes clearer as we do experiments. Now it's of course clear, but from what I said here, of course already a controlled not operation that looks at this thing and stores the other thing in a memory cell. And of course the memory cell is again a quantum system. It could be a memory cell of a quantum computer. Is in some way a version of this thing. So we can at least, what we can do is design a measurement device in a way that clearly the evolution is indeed like that in a verifiable way. So what do I mean by a verifiable way? So in principle, we could now go and check the total system DS and do a measurement or tomography on that state and see that it is indeed in that state. So from today's perspective, it's much more natural to say, this is actually fine to describe it like that. Of course, we wouldn't say that this was wrong. But this is just to tell you that today we have maybe a clearer view in this particular case. But now what I want to do, and this is really where the agreement stops, is you could of course go further and ask, what if you put the cut here and include the observer into the system? So this is kind of in some way the third variant, where I would have SD and the observer, and the cut is somehow outside. I don't know what is then still on the right, but that's a possible view you could have. It's kind of a view that is very natural if you don't want to assign anything special to humans, or there's something that distinguishes humans from other measurement devices. Now what Wigner, for example, clearly said is that this shouldn't be. So and clearly we are here. And he argued as follows, and I will now demonstrate this argument in a bit more detail. He said that, of course, we could actually do this experiment, and we know we see one outcome. We know we are not in a superposition. So therefore, this description here, if I applied it to this more static situation, would also include here the observer cannot be true. So I will now go into that in a bit more detail. But I hope this is now clear. So much of what I'm going to tell you is about this thing, this question, or this is kind of the origin of the discussion, which sometimes has labels like the measurement problem or the problem of the shifty split or shifty cut. Yes? Oh, yes, that's a very good point. So you could say maybe there is not this is not a binary thing. We shouldn't maybe call one thing classical and the other one maybe it's kind of a degree of quantum or classical. This is certainly a possibility, and which, however, so maybe we should come back to this question a bit later, because what I will tell you next is that we could in some way also say, actually it doesn't maybe matter so much. This is just a terminology. I mean, so far we have just two different ways of applying the formalism, and as long as the formalism at the end gives us the same results that we can experimentally observe, then it's just something we make up in our mind to think about the problem, but it's not actually relevant. So what I'm going to tell you maybe at the end of today, or certainly tomorrow, is that it actually makes a difference in certain experiments in an observable way, how we think here. And maybe we can then come back to the question and ask ourselves, what would it mean if now the system is somewhere in between classical and quantum? Because at that point it will also be clear what I actually mean really by classical and quantum. This was still a bit vague. I used this notion in a very informal way. But I used it in maybe a sufficiently clear way that you could at least see that, I mean, what I mean so far, maybe it's just a distinction between 1 and 2. So I know what to do in case 1 and I know what to do in case 2. If you now tell me what is in between, I wouldn't know what to write. So in that sense, I would already be in trouble if you say, what if T is a half classical, half quantum system? Which is now the correct formalism to describe it? I wouldn't know. So in that sense, it's going to be difficult to not because we have really just two formalisms. And so far the distinction is really about which formalism do we apply. Yes, so you could say we have two formalisms and we cannot mix them. So that would be maybe one possible answer to say it's unclear what it means to mix two formalisms. We have two formalisms to describe a system. One is the classical formalism, the other is the quantum. And we have to decide for one of the two because we don't have a formalism. Yes, please. Yes. Yes. So, okay. Yes, so, okay, so far what I did is just, I used, or maybe I should draw a little diagram which is maybe answering your question. I will come back to you just in a minute. Oh, there's no, okay, maybe that was not, I should have started with the thing on the back. I hope it's readable if I write here up to the, yes, but it's just, oh yes, good, yes, thanks. Fine. So, the way you could think about this thing is the following. You could say, on the one hand, we have kind of physics, which is in some way, okay, I use this term now vaguely, but it's the things we actually do in a lab and can observe and so on. On the other hand, we have what I call the mathematical formalism. This is just mathematics. Now, what is in physics? So in physics, we have measurement devices which show us stuff. So this is, for example, something is clearly situated here. If I do a measurement and I see an outcome, this is in physics. However, for example, ascribing a state to a system. So if I say, oh, there is this state, alpha up plus beta down. This is clearly something that is just a mathematical formula. There is no experimentalist I'm aware of who has ever seen a wave function in his lab. This is just not observable. This is a mathematical concept. Now, in some way, of course, to use quantum theory, at the end we want to do physics, we need to make a connection between these two things. So in some way we need to say, if we have a certain physical situation, how do we describe it with the mathematical formalism? So we somehow need this thing. So this is kind of say, some people call that the interpretation. We have a wave function, we need to know what it means. Now, you see, the Born rule is kind of a way which establishes this connection. Because if you don't have the Born rule, there's no way you can somehow tell what does this thing now mean. So I would still actually see the Born rule here in some way. That's part of the, you can add it to the mathematical formalism. It's still a mathematical statement. It says, for example, the probability of Z being plus 1/2. So this is a purely mathematical formula a priori. So it says this. That's just mathematics. But now I have a statement about Z. It's no longer a statement about the wave function. So now it's much easier to connect. So now I get a statement about Z. Now I can more easily connect these things. So in that sense, I would say the Born rule a priori is just a mathematical formula. But now, usually we use it in order to actually connect physics and observations. So that's kind of the use of Born. I hope this answers your question. So in some way, so you asked whether it's an axiom or not. So, okay, if I want to apply the formula, so in some way, and yes, it's an axiom in quantum mechanics, because if I now give you this state and ask you what is the outcome, then in order to answer this question, you need something in addition to the description of to the wave function. You need something. And so it's in some sense a postulate of quantum mechanics which now tells you what happens in this situation. Otherwise you wouldn't know how to deal with this situation. So you need this as a postulate. Okay, you had another question, I think. Yes. Yes. I will come to that. So the question is, I said experimentally I can in some way check, okay, I didn't actually say, or I didn't want to say I can distinguish one or two. What I wanted to say is, in principle, I can go to a lab, and if the measurement device is a very simple one, maybe a control knot type thing, then I could in principle check whether indeed after carrying out this p-knot thing or this measurement, the state, the joint state of the spin and the device is indeed in that state. That I can check. This wouldn't necessarily falsify this view. That's important. So I can just check whether this is a correct description, but it doesn't necessarily falsify this. Yes? Now the distinction between 2 and 3 is something I will go into in more detail later. So let's just postpone that a bit, and please ask again if it's not clear later, but that's a good point. That will be a main point of what. Yes? That's also an excellent question. So in situation 2, do I need the Born rule? So yes, if I only have that, then again I'm in this situation that I have now something within this mathematical formalism. I have now a state. Now in this case it's a state of a bigger system of S and T. And now to say what does this state mean now? Apart from just being a mathematical expression I can write down, I again need the Born rule. For example, if I want to do this test that I just mentioned and measure the joint system of the spin and the device, then I would need to do a measurement again from the outside. And then, of course, to say why should it now give a particular outcome, I need the Born rule again. So yeah, that was kind of the point of this thing, that the Born rule is somehow something I need to make the connection between the mathematical formalism and physics. But actually, things we are going to discuss will have a lot to do with this connection. So there are people, so actually the different interpretations of quantum mechanics differ in how they relate the mathematical formalism, which is in most interpretations the same. They don't introduce additional formalism. How they relate that to physics. So that's what distinguishes different interpretations. And you could say, there are people who say quantum mechanics doesn't require any interpretation. What they mean is maybe a minimal interpretation still, where they say, of course, there's still the Born rule which tells you that there is a certain outcome. So in some sense, it's still an interpretation of the mathematical formalism. And by the way, even in classical mechanics, you need an interpretation. For example, if I have a planet, a system of planets, there's the Sun and Earth, I could say, how do I match that? So that in this case, we would here have actually planetary systems. This will be, let's say, the Sun, and here the Earth, and then it will be somewhere Mars. And now I have here on the right, so this will be the analog thing for classical mechanics. On the right-hand side, I would have the mathematical objects that occur in classical mechanics, like the mass of a point, maybe its position, maybe its momentum. And then I have Newton's equations, which would give the evolution and so on. In some way, I still need to match these purely mathematical objects to physical reality. And I mean, physical reality now in a vague sense, but to the things we actually observe. And in some way, you could say this is also an interpretation of the mathematical formalism. Of course, it's so obvious there that we don't usually talk about it, and there's not much dispute. You can, of course, ask whether it's correct to, for example, describe a planet as a point mass, but we understand that well. We know it's a very good approximation if you have large scales and so on. And so here the interpretation is pretty clear. The big trouble, in some way, with quantum mechanics is that the match between the mathematical formalism and physics is not clear, and there are very different opinions about that. And foundations is a lot about understanding that link. Now, as I said, the interpretations really give different answers. And by the way, it will not be the goal of this lecture to convince you of any of particular interpretation that exists. There are many. Bohmian mechanics, there's consistent histories, there's many worlds and so on. I will not favor any of them. Actually, the message will rather be that any of them has its own problems and major problems. And it's probably your task, once you have learned all this, to develop a much better one than the ones that exist. So I will rather use the existing interpretations to give you examples of how these connections could be made. But indeed, much of my lecture will be about this connection. So the mathematical formalism quantum theory will not be changed in most of the interpretation, except maybe for collapse theory, add some collapse mechanism. Okay, are there more questions about this? Yes? Pardon, I didn't get the beginning of your question. Aha, that's also an excellent question. Yeah, so do I need a classical system to apply Born rule? So here, again, the different interpretations differ in what answer one would be. Most or let's say at least the conventional interpretation, which doesn't include, for example, many worlds and so on, they would always say there needs to be an outside classical system, which is the ultimate, some people call it the ultimate measurement device, which is somehow outside of the quantum system. So we cannot model the whole world as a big quantum system because there's nothing outside, and then all statements become empty statements. But this view is not shared by all interpretations. And for example, in many worlds, the Born rule has a much more subtle meaning where it's about perceptions of someone who is in this wave function, but there is no outside system. We will come to that as well. But yes, that's another example of a question which has no answer where physicists today would agree. That's why I said there are many open questions here. But what I want to do is actually not to leave them as philosophical questions where you just can have different opinions, but to turn them into actual physical questions which are at least in principle testable. That will be the goal of all this. Yes? Yes. Yes. So actually, the reason why I drew them both ways is that usually we have like a physics problem we want to solve. So we start on the left-hand side, but in order to solve it, we translate it into the mathematical formalism. And we do that in the case of planets. It's very well. No, I mean we observe planets. Now we assign these numbers to them. We assign coordinates to them, which is now the translation. Now we do a calculation. We apply Newton's equations or Lagrangian mechanics. And then at the end, once we have an answer here, we want to translate it back into a physical answer. So in that sense, that's what I meant by it goes both ways. So we use, okay. So thanks for asking questions. I think it's important that you understand it to this point because it's not, so there will not be so much I'm going to tell you, but I hope that at least these things that I will tell you will be very clear at the end. That's more important. Okay, now, if there are no further questions, I will now proceed with a small discussion of Wigner's argument. And this is you could see that as maybe a historical note, which is, however, going to lead us to something more interesting, which is even relevant today. But how did Wigner, who was clearly one of these big fathers of quantum mechanics, argue? He kind of considered somehow this third thing versus 2 and 1. So what did he do? He looked at essentially the same experiment. Of course, these systems are all exchangeable. Instead of a spin, you can take another physical system with 2 distinguishable states or even more. So that's not going to make a difference. But what he did is the following. He looked at, again, this thing, but he explicitly included the observer. And I will from now on call an observer an agent. There are different names of that. But Wigner just thought of it as an actual person. And I will later be a bit more, try to be a bit more sophisticated about what I mean. But Wigner just thought about actually, for example, his friend who is carrying out the experiment. So the setup he had in mind was, roughly speaking, the same here. So we have the spin system, we have the measurement device, like that. And we have initially in the ready state, but we have now, and this is traditionally called the friend, Wigner's friend. He in his paper really talks about his friend. And so this is just the person who actually carries out, okay, maybe I will here put an F inside because later I'm not very good in drawing, as you can see. But what I want to do is here to have the friend sufficiently large so that on his pullover there is an S, on her pullover. So he considered this setup, and the only task of the friend is to actually read off the outcome of this measurement from the device. And now we can again do kind of two different analyses, but the analysis he considered was now the one corresponding to the third, or to the consequent extension of this particular thing. So he said that, let's suppose this spin is again in an arbitrary state, S, which could be a superposition, and I will not always write this superposition. Let's always assume it's alpha up plus beta down. And so this system here is now in the state, so he looked at the whole thing now as a big quantum system, so the device is in a ready state, and he said, let's suppose as an assumption, I mean at the end he didn't like this assumption, but he wanted to kind of argue that this assumption is wrong. But let's now, maybe in his view, there would be a kind of an argument by contradiction. Let's by contradiction assume that even the friend is a quantum system. So maybe the friend is now also ready to do the experiment, and I indicate this by state F. So I treat the friend in the same way as I would, or Wigner treat it as the same way as I would for a measurement device. And now I have the time evolution. And now, okay, there's nothing surprising as if you have now followed so far what happened. Of course, the final state of these three systems will now be bilinearity with the coefficient alpha, the spin will be up. The measurement device will show +1/2, and the friend will know that it's +1/2, and they indicate that also in that way. So this state here, that's maybe a bit tougher, to be the state that the friend is in the case where she observed +1/2. So then she's in a certain state. You could say this is the state of her brain when her brain has recorded that it's been up. Plus now, but of course because of linearity, there's now this down thing. Okay. This is hopefully from what I said so far clear. Again, this is based on the assumption that we treat the friend as a quantum system. And Wigner now said, of course, the friend, we could even, okay, what he said is we could even think of this whole experiment being carried out in principle in a perfectly isolated lab. So we could kind of think of here a container, which I call L for lab, and this whole container is just one big quantum system. So it's a tripartite quantum system. It consists of S, D, and S. So maybe later, if I use this formalism, I would write L is in some way the tensor product of S, D, and S. So that's just one big quantum system, and it evolves in some way. You could even think of the friend is in a perfectly isolated lab. Now what Wigner argued is we could, of course, later open the lab and ask the friend, did you already, okay, this is again time t0 and this is time t1, it's continuous from above. We could ask him, maybe at time t10, we open the lab and ask him, what did you see at time t1? And we know, of course, that the friend will tell us, yes, I saw actually either spin up, or he said, I saw spin down. And we also know that if we were the friend, we would see spin up at time 1 and spin down. We will not be in a strange superposition state. We just know that from daily life. Whenever we do a measurement, we see either up or down. It never happens to us that we see something blurred if we do the thing correctly. So Wigner argued, therefore, it cannot be that this is the correct description, because according to this description, the state of the friend is not either that he has seen +1/2 or -1/2, but it's something in between. You see, the way I already talk about this is maybe not very convincing. And indeed, what Wigner did is actually, so he really argued like that. He said that it cannot be that the state is like that because the friend sees either that outcome or that. So it must be that this wave function somehow collapses either to this branch, so to speak, or to this part of the superposition. And he concluded from that, as you can read when he read his original paper, he concluded from that therefore it cannot be that a big system that includes living objects, like persons, evolves according to the laws of quantum theory. So his conclusion was really quantum theory cannot be a universally valid theory. At least it has to stop to be valid when we consider big systems. That was his conclusion. And today this is maybe known as the collapse theory. I think he was even arguing about consciousness. He said as soon as there is some conscious object, or conscious object is maybe then the wrong word, but some conscious person inside this thing, then the laws of quantum theory stop to be applicable. That was his argument. Now let's just argue see what happened later, because of course not everyone accepted this argument. And maybe it's important to see what were the assumptions that Wigner made. Does anyone see what? So when you want this to make this more precise, what assumption did Wigner actually make? And maybe you should think of this thing here. He somehow implicitly makes certain assumptions, or maybe not so implicitly. He makes assumptions about how the physics connects to the mathematical formalism. So does anyone see what assumptions he needs to make to really arrive at the conclusion that this evolution can in reality not be unitary? So his conclusion was this evolution cannot be unitary evolution. So what assumptions did he actually make? Yes? Yes, so I'm not sure I understood it. Right. So you said if the observer is, so yes, the observer is now entangled with the system, and what did you say then? Yes, right. That's kind of, so he somehow says that there is really a connection between the state we have, so in some way, maybe if I do it here, that's right. So he said there must be a connection between the state of the system and actual perceptions. That's right, that's what he assumed. Maybe I will list these assumptions somewhere, maybe here, because we will later argue about that. So actually, maybe I will put two assumptions. So one assumption is which is a difference. So yours will be the second one. One assumption is that you even need to start talking about these things is that the wave function we assign to the system is really like a physical object which is unique. So there is a unique, so in some way, there is a unique wave function assigned to any physical system. Because, okay, that will be, maybe I should, it's not so clear what that means, but I will later contrast it to a view where many people have, a modern view where they say the wave function which we assign to a system is personal, in the sense that you could assign a wave function to a system which is different from the one I assigned to it, and we are both right. This is, here he clearly makes the assumption it's a unique thing. It's like physically well defined. It's not a matter of opinion. And then the second assumption is indeed that if so, and I could phrase it like that, if observer, or if the agent observes set plus 1/2, she is in state maybe it's if and only if that even assumes is in state state plus 1. So this makes sense because that's kind of a connection between so somewhere you need to make the connection between the mathematical formalism, which is the state, and what you perceive. That's necessary. I mean, without such an assumption, you will never be able to say anything about the world. And he made this assumption, said the state of the system corresponds to, so if a person is in a certain state, then this must correspond to what the person actually perceives. If he sees this outcome set plus 1/2, then he must be in that state. Okay, so these were the two assumptions, and you can see that if you really make these two assumptions, then you arrive at the contradiction to I would say, experimental fact that if we observe something, we indeed see one outcome. So under these two assumptions, Wigner's argument is, I would say, correct, and one must conclude that such a big system cannot evolve unitarily. Now, of course, few people were ready to kind of accept that big systems should not evolve unitarily, because after all, even less today, because experimentally we have verified quantum mechanics to an enormous precision, and we know all the little ingredients, all the constituents of this big system, all our atoms, they're governed by quantum theory, so it's kind of natural to say that this doesn't somewhere stop if we have conscious or living objects in this. I should say this is not very, we can at this point not really do experiments with complex systems of that kind. And by the way, that's why it's today very exciting, because if we build, for example, a universal quantum computer, we have in principle a system which is, let's say, a scalable quantum computer. Then we have a system which has at least the same complexity in principle as that system that I have here. So that's, by the way, one reason for me to build quantum computers, apart from the applications, which I find which are also interesting, but I think for me, building a quantum computer is like a big experiment that we do, for example, in Europe when we do the particle collisions at CERN. It is a huge, enormously expensive thing. Building quantum computers is also very expensive, but it also has the purpose of giving answers to certain fundamental questions. The fundamental question that quantum computers answer is the question whether complex systems still are correctly described by our current formalism of quantum mechanics. And in some way you could therefore say, and this maybe answers a bit the question that was asked before, building a quantum computer could help us answering this question. Of course, Wigner would still argue a quantum computer is not a living object, but at least it can answer it in the way that if you have a system that is equally complex in principle as the system I've drawn here, quantum mechanics applies, then it's becoming very difficult to argue that there's now a distinction if the system is a human as compared to not being a living object. Anyway, so I think the point here is quantum computers will answer in some way the question whether big systems such as this system or very complex systems evolve still unitarily. But it's not answered yet, but I think most people don't doubt that this will be the case. Yes. 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 That's also a good. So what I could test here is the following. So here is a prediction of what is the big state of the system, the device, and the friend in total. So it's a big superposition. So what I would need to do is I run the quantum computer, I let it do that, so I simulate kind of the observer. So it's a very difficult experiment. I kind of simulate the person observing the measurement. Now the question is, what does it mean to simulate the human? But I just want to do something equally complex. Maybe in principle, to do it optimally, I would simulate the whole brain of this person. At the end, I could actually measure the state of the quantum computer. And if the quantum computer is in this superposition state, which most people would expect to be the case, then I have verified that indeed this evolution was as prescribed by unitary quantum. So I just measure the state in a basis which includes this state as a measurement basis. It shows that, so what it would show is that the system equally complex as that. Don't say, I'm careful here, I'm not saying it's really the same as a real human observer, but an equally complex system is correctly described by this state, which is what Wigner denied. So Wigner said here there must be a collapse to one of these states. So we could falsify Wigner's prediction for a system that is equally complex as the system that Wigner considered. And I'm just stressing, although most, I think, so maybe I should just make a quick, so who would think that if we do this experiment now with a quantum computer, not with a human, who would think that the outcome is indeed that we will be in this state? Who thinks it's not the case? You see, that's really the situation we have today, that essentially no one thinks that this is not the case. And so this, maybe I will ask this question at the end of the third lecture, because we will see that if we assume that we run into other problems, which are, okay, I will come back to that, but I will just ask this question again and then see what the answer will be. Yes? So here indeed there is no, so here quantum theory doesn't make a distinction as far, I mean, ordinary the formalism of quantum theory, let's say this side, has no element which tells us there is a difference between a small and a big object. By the way, this would change if I had the mathematical formalism of a collapse theory. They have an additional rule which indeed makes a distinction between, in some way, small objects and large ones. I mean, the distinction is, of course, not phrased in that way, it just has an additional term, for example, in the Schrödinger equation, which then has the effect that large systems behave differently than small ones. But ordinary quantum theory, as you learn it, there's no rule which says, if the system is bigger than 10 to the 20 atoms, this rule doesn't apply. There's nothing like that. So in that sense, I didn't have to care whether the system is large or not. So the point is, this is really what the formalism tells us. But Wigner kind of argued this cannot be, because it would be in contradiction to our perception, which we have that there is indeed one outcome. Okay, no, his conclusion was really because the problem only arises. So this is important. So what he sees here as the physics is really the perception that we as agents. So we have perception. And this is something we can verify very directly. We have actual perception. So he said, at least that's why he went here to a friend and not some mechanical device. He said, we know the perception of this person will be either plus 1/2 or minus 1/2. We know that from experience. So the way this person enters into Wigner's argument is really by the fact that we know that a person has an actual perception of being plus 1/2 or minus 1. If this was just a mechanical device, this would not be the case according to Wigner. So in that sense, we cannot directly falsify Wigner, because he may still argue a quantum computer is not a living object with a perception, but we could at least, I mean, I think that many of the modern views is just, it has to do with the complexity. If you are as complex as humans, maybe something strange happens, potentially. But as I said, most people like you don't believe that. So I think the common belief is that this would indeed happen, even if we had an actual human in this thing. Of course, it would be extremely hard to do the experiment. By the way, I should say, what I will just come to your question. So this will be important as well. So we are in the following talking about thought experiments. And what do I mean by a thought experiment? The thought experiment, the purpose of a thought experiment is to test in some way the consistency of a physical theory. So we are maybe talking about things which are very hard to realize in practice, like I'm testing this state. This is very hard to realize, but crucially, the physics doesn't prevent us from, so there's no law of physics that tells us there's something wrong with this evolution. And this is something we often do. I mean, Einstein did that all the time. For example, when we are talking about black holes, we can ask what happens if we cross the event horizon. We know not much happens, but this is anyway just a thought experiment, because I think it's completely unrealistic to come close to a black hole and do the actual experiment. And the same is true for what I mentioned before, the black hole information paradox. There we are talking even about collecting all the radiation from the black hole. That is probably completely unrealistic. Nevertheless, it tells us a lot about the structure of physical theories, and that's what this is all about. Because if there's a problem, we know something must be wrong with the theory that describes reality. So in that sense, I don't care about the feasibility of the experiment. What I care about is the consistency of the description of the real world. And if a thought experiment shows me that this is not consistent, then I'm worried, even if I cannot actually carry out the experiment. Okay, yes? Right. This is the next point. Now I will actually discuss what people say against these things. And it's absolutely right what you're saying. There are many, actually most interpretations of quantum mechanics have been developed after Wigner talked about this experiment. And so most interpretations claim that they can deal with this situation and there is no problem. And many worlds is one of them. was another question from the back. Hold on. Oh, here, yes. Mm-hmm. Yes. Yeah, so your question is what is really the difference between the friend and just another device? So as I said, I think the distinction is really that the friends could be us, and we know we have the perception of an outcome. You see, this really makes a difference because at the end of the day, we want to talk about things we actually see. I mean, this is the whole. I mean, if you say you deny any physical reality, at least what we should talk about is things we can at the end observe. And so I think the reason why Wigner introduced this friend is really that he wouldn't be able to say what we would expect if this was a device. But we know that if we are this person, we will see something. So he uses this fact, and if you replace this by a machine, you can no longer argue that the machine sees something. I think this is the only reason. He really wanted to... Yes, yes. But we need, I mean, this is crucial because you see, when we want to make the connection to, I mean, okay, it's probably hard to see actually from here, I just realized, to physics, we need at least something which we can talk about, which is relevant to us. And so maybe the most basic thing we can talk about is the perception we have at the end. But even before we make any other assumptions, we know we have certain perceptions. So Wigner made this, he introduced the person to make this connection to physics and to say now, because there's a person, we know he has a perception. And I think many of these measurement problems are right. So if we didn't have the perception of things, we wouldn't have this measurement problem. We could just say, the state of the universe is described by a huge wave function, and that's it. And we wouldn't need to bother about anything. That would just be a completely, perfectly fine theory, but it wouldn't tell us anything, of course, because it wouldn't theory. It would really just be a mathematical description. And somewhere we want to relate it to what we perceive. That's this element here. I think it's unavoidable in some way to at some point talk about a measurement or a perception to make this connection between mathematical formalism and physics. And the minimal thing to talk about. Okay, now what are the arguments? So, and this will lead me actually to an interesting part, because now the modern, let's say, research on foundation talks really about how can we exclude certain possible, okay, I mean, when I now talk about interpretations, it's really about how do I make connections between this and that. And I will start by giving you some examples of that. And a lot of the research, starting actually already with Bell, or maybe even earlier, was about, with EPR and so on, was about excluding certain possible ways of interpreting the mathematical formalism. And still, that's what we're doing today. So more modern arguments, like an argument about, which is called about the reality of the wave function, PBR argument, maybe I've heard of that, are also about that. So many of the actual, so these are then theorems, so they are not that important. So we really want to make hard statements. They are statements that try to rule out certain ways of connecting physics with the mathematical formalism. So but in order to motivate that, I will start again with these assumptions. And there are essentially two, because there are two assumptions, there are kind of two ways you can avoid Wigner's conclusion. One is to give up the idea that there's a unique wave function assigned to physics. And this is something people call sometimes the epistemic view. And okay, to illustrate what that means, very briefly, is that it's the same, you interpret wave functions in the same way that you would interpret probabilities, at least if you have kind of a Bayesian viewpoint. So what do I mean by that? So what could we say here? So if you have, so what would be a way to not assign a unique wave function? That's actually the way we could do, if I now go back to this thing that I had earlier here. Oh, not here. Yeah. Just write it. I hope it's still done. I didn't erase it. Okay. Maybe I'll just do the following. I will briefly write here a possibility of what one could do in the two cases. So, you know, we had before two ways of cutting the thing, which was to have, so this was the view where we had the spin and the friend. So here we could say the friend can, and maybe the measurement device can be on either way, that doesn't matter. So we can ask, what state does the friend assign to the system after carrying out the measurement? Say, if f observes z equal to plus 1/2, she assigns state to x. So that's something that is quite natural. So the system is in state plus 1/2. That's what you would do, actually. I mean, if you are this friend and you have seen spin up, you would say, of course, now this if you have measured z plus 1/2, you know the spin is now in state 1/2. But if one has to cut in that way that s and f is part of it, and let's say, I call him Wigner. So Wigner is still outside. So we could say, what state does Wigner, who is outside, assign to it? He says that the state of the system, let's say, if the initial spin, so if initial spin was, and let me maybe now introduce this term convention to say the spin right should just be 1/2 up and 1 square root of 2 down. This is just a convention. I could also have a minus sign, but let me use this convention. Then the big state of the system, the measurement device B and the friend, is the state that I've written down before, which is essentially this big entangled state. Maybe I'll abbreviate it a bit here. So it's this state here. So we have two different states assigned to the system, and it's okay. Now they talk about different systems. One talks just about S, the other one talks about joint system of everything. But I could even trace out the thing. So what is the corresponding marginal state on rho? Does anyone know that? So if you assign this big state to the system SES, what is the state you assign to S? The mixed state of rho. So what is the density operator that describes that? Right. Yes. Right. I think you mean the right thing. I saw where you said it. That I think you mean that. Yeah. So that's the state that one would assign to the system. And now you see, F assigns a different state to the system. Once he has seen this outcome, he assigns the state up to the system. Wigner assigns a mixed state to the system. And now those people who take this so-called epistemic view, they would do the same. They kind of do the same thing as, okay, I don't have a coin here. Let's suppose this is a coin. I could toss a coin here. Now it's either heads or tails. Now I could look. Now what is the state that I assign to this system? I have looked at it, so clearly I assign now a definite state. So I don't tell you which one, because I could also ask, what is the state you assign to the system? And you could now say, you could use probability theory to say the probability assigned to the system is that with probability 1/2, it's tails, with probability 1/2, it's heads. So you assigned a probability distribution of 1/2, 1/2, whereas I actually only assigned the probability of 1 to heads because I've already seen it. And so we have assigned two different probability distributions to the same system, but we are both right. The only distinction was that we had different initial information about, or different information about the system. So my probability distribution of having 1 for one outcome and 0 for the other just reflects the fact that I'm sure what it is, whereas you don't know it. And so the epistemic view of quantum mechanics is the same thing just for quantum states. They say they're both right, they have just different amounts of information. And that makes sense. Indeed, the friend has seen something that Wigner hasn't seen. He has seen the outcome z plus 1/2, and therefore she can assign pure state to the system. She knows it's up. whereas Wigner hasn't seen this outcome. That was in the closed box. And therefore, she's uncertain what the spin is, and it's 1/2, 1/2. So that's the so-called epistemic view. And it, you see, it kind of resolves the thing because it just says assumption 1 is not correct. It's not, one shouldn't think of assigning a unique wave function to the universe. Wave function is has to reflect the knowledge we have about the system, and if you have two people, two agents with different knowledge, they assign different wave functions to the system. This view that is reflected by 1 is called the ontic wave function. So there's really a real wave function of the world, and we cannot assign different ones. Maybe the same way as you think of an electromagnetic field, there is a certain field strength somewhere, and so we have to agree what the field is at the particular point. So of course we have to agree on a reference system and so on if we want to give coordinates, but that's the usual way we talk about classical electrodynamics. We know at every point there is a certain field strength and we agree on that. We cannot say this is depending on the observer. It's a direct physical value. So that's the ontic view. And one could use the same for quantum mechanics, and that's what Wigner did. The epistemic view is to say this is really more like a probability distribution, and it depends on the observer. So this is one way out, and that's, for example, I will come back to the actual interpretations. That's, for example, the way out that people take that follow cubism. That's a main ingredient of cubism. But there are also other approaches, like even certain people call it the modern Copenhagen view. There are people like Joseph Brugsen and so on. They say also it's natural always to consider the information we have. Also, there is something called relational quantum mechanics that has been developed by Carlo Rovelli. So it's a very widespread view, this epistemic view. And I think it's very natural from a quantum information perspective, where we anyway naturally think probability distribution. But again, that's a choice, and as I said before, I don't want to convince you of one particular choice. That's one possible way out among others. Yes. That's a good, so it will be very interesting to actually compare the different views one has about the different interpretations, what they say about certain experiments like the Bell experiment and EPR. I will come back to them. I don't want to do it right now because I will have to introduce the correlations and so on, but I will certainly answer your question. And otherwise, if it's not answered until tomorrow noon, then please complain. Then I will still have a chance to explain it to you. But yeah, so that's actually the reason why we look at all these things, like Bell experiments, to compare these interpretations. Now, obviously there is also another way, because I wrote here 2 assumptions. You could also say, let's try to give up 2. And that's, for example, in some way what many worlds do, and also what Bohmian mechanics does. I now don't want to explain what is exactly many worlds and Bohmian mechanics. I will do that maybe later in a bit more detail, but it's not the goal here to explain to you Bohmian mechanics. The rough idea, however, is to say that maybe these people say quantum mechanics is not, or the Bohmians, for example, say quantum mechanics is not a complete theory. So, for example, it can be that we assign to a system that state. So a Bohmian would say, indeed, you have this evolution, that's correct. But it's not now the case that we can read off from this state what the agent observed. The Bohmian would say there is an additional element to the theory. Some people call it a hidden variable. In Bohmian mechanics, it's indeed some hidden position, for example, where the particle lies. And so there's some additional element to the theory apart from the quantum state that tells you what the observer actually sees. So in this picture that I had here with comparing the mathematical formalism to physics, I would say what the Bohmians do is say, okay, there is indeed this quantum state and so on, but in addition, we have here some hidden variable. They don't necessarily call it like that. And this variable, for example, tells us what is set. So, or maybe it's a hidden variable, let's call it, it's usually called lambda. But in order to now tell what is actually the observation, we need to combine the hidden variable and the quantum state. So the hidden variable, if you look at it, determines, for example, Z is plus 1/2 or Z is minus 1. So the essential idea is that to say, indeed, from reading this state, from just looking at this big state, we cannot say what it is, but we have just not a complete theory. There is this additional element which tells us what the agent sees. And depending on that value, he sees either plus 1/2 and minus 1/2. So this gives up this thing. So it doesn't give up the fact that, so still a Bohmian would say, of course, the agent observes either plus 1/2 or minus 1/2, but we shouldn't expect to see that in the wave function, because the wave function is just only a partial description. We also need to look at this hidden variable. So this is the way it resolves it. Many worlds does in some way almost the same thing, except that it gives up the hidden variable in some way. So it says, indeed the wave function is there, but an observer will see either plus 1/2 and minus 1/2. So there is this additional element, but it's not part of the theory, and therefore we cannot, I mean, you can now think in different ways about it. Many worlders would typically say this just means there is one branch of the universe in which the observer sees plus 1/2 and another in which it's minus 1/2 if you have actually this wave function here. And of course you could say in each branch, so the branches are kind of labeled, you could label them, and this would correspond to the hidden variables. Anyway, I don't want at this point to go more into these interpretations. So far the message should be that indeed there are different directions of overcoming Wigner's argument, because Wigner's argument necessarily tells us there's something wrong with our current formalism of quantum mechanics, and as I just saw here, no one believes that. So you certainly want to give up one of these two assumptions, and indeed that has been done in the literature. So the epistemic view gives up this, and the, for example, Bohmian or many world view gives up that assumption. Yes? No, okay. The many worlds, okay. I should say that there are many worlds views, depending on which proponent of many worlds you talk to, probably have different answers. But let's say the view of, I would say the majority of people I talk to, which is maybe not the majority of many worlds, would say that they would replace here any physical system by the whole universe and say there is one big wave function that describes the whole universe, and everything that happens is described by that, and we look at each branch. By the way, the Bohmians a majority of the Bohmians would also do that. They would not assign a wave functions to certain subsystems of the world. They would say there's a big wave function of the universe, like the big electromagnetic field that is defined on any point of the universe. Yes? Aha. So the question is, in epistemic view, when do you do what? So there is just, you have both possibilities, and we saw at the very beginning, we can in principle treat the system as classical or quantum. So if you have an epistemic view, you still have this freedom. You can say a system is a quantum system, and then it has a quantum state, or you can treat it as a classical system, and then it has a classical state. The epistemic view doesn't a priori tell you that you have to make a choice in between them. Of course, if you want to talk about superpositions, you need to describe it as a quantum system, but I would say there's nothing wrong if you have a system where you only care about a certain basis, let's say classical basis, like what's typically the case. If you talk about the measurement device, then you can also use the formalism of probability. Yes, yes. So indeed, if you have a spin and you describe it as a classical system, you have limited yourself, and you can no longer talk about in the formalism what happens if you measure it in different directions. So indeed, when you want to do, for example, make considerations what happens for different measurements, you're forced to use the quantum formalism. But that's fine. I mean, that's, I think, not. Aha. So you could see in the epistemic view, you can just say the probability distributions are a special case of a quantum system. So it's just a more, let's say, economical way to talk about the state, because you essentially only talk about the diagonal elements of the state. You could see it like that, and then in principle, I think most of epistemic theories are such that you can in principle treat any arbitrarily large system as a quantum. Yes? So, mhm. I'm not sure so of course if you repeat the measurement with the same system, we will always now see the same. So so for example, if we are now in this state here, and now let's suppose the friend makes another measurement on the system. He will kind of add, let's say he could even use a second measurement device. What I would do in the formalism is I would have the second measurement device would also show z plus 1/2 here. And in this branch it would again show -1. So if I repeat the measurement on the same system, I will get the same outcome, and I could reflect that here in these branches. But I'm not sure I understood your question correctly. Mm-hmm. So what is the experiment you have in mind? Or you think you do a second measurement now to the outside? Or yes? Aha. So if you apply a measurement to this whole state from the outside, let's say Wigner now applies. Oh, yes, okay, now I understand your question. So you could really think of this like there is this overall state, and now Wigner comes and applies the measurement from the outside, which he could easily do. It just has to open the box. This will actually, and look, what is that thing? So then, indeed, what quantum mechanics would now tell us is with probability alpha squared, he will find the friend seeing z plus 1/2, and the measurement device shows 1/2, and the spin is 1/2, and with probability beta will be that, if he does that. And so, you see, there's nothing strange then if he does that in some way. He would just, in some way, I mean, it's just the usual way you would apply quantum mechanics and the Born rule. I think what is special is that he could also choose to do this much more complicated measurement in these bases. And if this state is a basis element, he will with probability 1 find that outcome. That's kind of the surprising thing. The fact that he could measure in this, let's say in the basis plus 1/2, -1/2 will just be like another thing in this chain. So before we had the spin, the friend, and so you could, I mean, there's this interesting thing that Bell said, by the way, and maybe I should conclude almost with that for today. So you see, there's a chain. There's the spin, there's the measurement device, there's the friend. And now I can say, Wigner is also someone who measures. There could be, I think Chatlav Bruckner has an example of something where he called that super Wigner. You see, you can continue. There's someone again outside of that lab. And so you can put the split everywhere. And indeed, it never ends in principle. You can always say there's again a person outside who views the whole thing as a quantum system. And whenever they measure in the same basis as these, there's nothing surprising they see. This is what we do. Actually, if you go to a lab and do a measurement, and then you come and tell me what the outcome is, this is really as if I was now Wigner and would measure you, but because I measure you with a normal basis in which you measure, people just at the end agree and so on. It's not so clear what happens to you if I measure you in this other basis. You better don't try. But then it's not, let's say, then I see something that would really distinguish that. So even if you now said it's already collapsed to one of them, we wouldn't see a difference. So this experiment cannot tell us a difference because from the outside it's just filled with that probability. So actually Bell has this interesting citation or funny citation where he says, we can really never put this split because it's unclear whether already, I mean, for example, a cat would be sufficient, whether we need a human. Then he said, maybe we need even a human who already completed his physics PhD, and only then it's a measurement. You see, he made fun of this fact that we can really not determine where we are. And so a theory, a physical theory, or an interpretation which doesn't tell us where to put the split, and essentially no interpretation tells us where to put the split, should better make sure that we are consistent, that we don't get contradictory results depending on where we put the split. And now the outlook to tomorrow is that we will see a situation where, at least on the face of it and with some very mild assumptions which are only operational, we will see that there are situations in which we are inconsistent if we put the split in. And then this will be kind of the example I will use to discuss different interpretations of quantum mechanics. So today I only mentioned them very briefly, but I will make a more slightly extended version of this Wigner's experiment. And this will be our object of study, which we will then study from the different interpretations viewpoint. And as you will see, any interpretation will locate the problem at a different place. And this will help us understanding what the different views are. So I will introduce this example mainly in order to discuss possible views, and probably you will at the end come to the same conclusion as I come, that none of the interpretations gives a satisfactory answer about what happens in this thought experiment. So I see that really then as a starting point for future research where we talk about open. So the topic of tomorrow will be to look at an extension of this experiment where I will argue that we cannot just shift this split without being extremely careful, and even if we are careful, or we will probably actually run into big problems. And that's, I would say, an unsolved problem, which we will discuss later, maybe then also on Wednesday. Okay, so thanks a lot for the many questions. I think it's really great if you help me up, because as I said, it's important that those things we discuss you understand really deeply rather than that we cover a lot of material. Okay, and then see you tomorrow.